Thank you very much. This morning, my colleague Yidong Zhong has talked about topological photonics. So here we're going to talk about topological physics for sound. It is actually Yidong who introduced me to this general field of topological physics. So really thank Yidong for introducing me to this field. Why we choose this topic for topological physics for sound? So if you compare it to the electrons and photons, then you can see that we don't have much freedom to control sound. So for electrons, you have charge, you have spin, so you can respond to the magnetic field. And for photons or electromagnetic waves, you can use the magneto-optic material to let them respond to the magnetic field. And you also have polarization. You can left-handed circular polarization, right-handed circular polarization to simulate the spin-up, spin-down states for electrons. But for sound, you can see for sound propagating through air, it's essentially a longitudinal wave, and you don't have spin to play with, and you don't have polarization to utilize, and so you don't respond to the magnetic field. So we try to develop this. I think that's the reason why the development of topological physics for sound is largely lagging behind compared to the development in other systems. But on the other hand, because this is late, it provides us an opportunity to look back at the history to help us develop new topological physics. And because this is late, and we can see that sometimes it's even the development here is even faster than condensed matter systems. So let's look back at the history. So in 1988, Prof. Haldane proposed the well-known Haldane model for the quantum Hall effect without Landau levels. So this is achieved by realizing a staggered magnetic field where you have magnetic flux, positive magnetic flux at the center, and then negative magnetic flux around the boundary of the unit cell. So the average magnetic flux is 0. So this quantum Hall effect without Landau levels, this is corresponds to the single particle energy band. So this becomes a major motivation for Haldane and his student, who now is an assistant professor in Stanford University. So this has become the major motivation for them to transfer it into photonics. So that was after 20 years later. So they transfer it into photonics with a similar effect. So there was then the MIT group, where my colleague Yidong was also involved when he was a student at MIT. So they modified the design, and then they realized it with a gyromagnetic photonic crystal. So this is a photonic crystal. You apply a magnetic field perpendicular to it. So you can see that for the electromagnetic wave launched to the right-hand side, this is robust to the backscattering against the defect. So after that, then you see that there are a lot of proposals, and the field of topological photonics is developing very fast. So there are a lot of development in the past few years. So now the question is, all right, can we follow a similar path for sound? So before we discuss on it, let's watch a short video. This is about a bathtub drain vortex. So bathtub drain vortex is like, this is a container where you have a hole at the bottom. So when you open the hole at the bottom, the water will flow through this hole and then form a vortex. So everybody see it in the daily life. So let's play the video here. So this is the water level here. All right. So this is a very beautiful video, and actually, this vortex was analyzed in Fermion lectures, volume 2. There's a figure over here. So in Fermion lectures, we imply the curve-free condition. The curve-free condition is the result because for water you cannot stand a shear force. So if you ignore the viscosity, so this must be curve-free. Then if you consider the velocity distribution in a local region here, then you can find that the velocity distribution must decrease as 1 over r. Here this c is a constant. So in other words, if you integrate the velocity, this is an integral. If you integrate the velocity of water around this vortex, it will be a constant c. So this constant is called circulation. This is the well known. And now in the video, you can see that the vortex is not that stable. It keeps swinging back and forth, left and right. So it's not good. So it's better to keep the position of this vortex by just putting in a rod and then let the rod spin. So everything is the same except that, okay, you need to put an extra condition that this velocity distribution is for the region r larger than the radius of the rod. So this becomes very similar to the Aharonov-Bohm effect, where you can see that this velocity v is very similar to the vector potential surrounding the solenoid, and this circulation becomes very similar to the confined magnetic flux inside the solenoid. So I think the first one who saw this kind of analogy is Michael Berry. So he and his colleagues did one experiment in 1980. This is for water wave. This is 4 years before he officially proposed his Berry phase. So this is the real photo. So this is a vortex here. So you can launch water waves on the right hand side, propagating to the left hand side. So you can see that because of the rotating of this vortex, you can see that the phase in the lower region is running faster than the phase in the upper region. So you can see that eventually there is a phase singularity along the line just behind the vortex. Just behind the vortex. So this is very similar to the AB effect. Now, our question: can we put a bunch of rods, let them spin at the same time, and then we can study a lattice of vortices? So the difficulty here is it's not a periodic system, and the Bloch theorem is not applicable. So we modify the problem to be, okay, can we study a lattice of confined vortices? So we can confine it by just, for example, you can put a boundary surrounding this vortex to confine it. For example, and this boundary is supposed to transmit sound but can suppress the airflow. For example, the cover of this microphone can suppress the airflow, but can suppress the wind, but or still transmit sound. So we can see for the boundary for this problem, you need to import a boundary condition where for the airflow inside this region, inside the annulus region, the velocity close to the inner boundary at R1 should be the same as the velocity as the spinning rod. And then for the at this outer boundary R2, then the velocity should be 0. So this is the boundary condition. Then regarding the airflow distribution in the annulus in between, so you can see that there's a very standard called curved flow here. So this is there are not many analytic solutions to Navier-Stokes equations, and this is one of them. So if we have concentric circles spinning at the same time, then you can see there's another solution for the Navier-Stokes equations. So when this omega-2 is 0, meaning that this outer boundary is stationary, then you can have a velocity distribution for the airflow in the annulus. So now you can analyze the sound, the acoustic waves in here. So we assume this acoustic wave is a small amplitude sound. So this you can treat it as a perturbation to the velocity, to the density, pressure. Here, this phi is the so-called velocity potential. So you can utilize the Euler's equation and applying the continuity, and then you can obtain a master equation. This is to describe the sound propagation in a moving medium. So it's amazing to see that such a formula hasn't been derived until 1990, and then we can do a change of variable and then convert it to the Schrödinger type equation over here. So this A is the effective vector potential. This V is the effective scalar potential. So it looks like for sound, it looks like the acoustic wave is propagating it's exhibiting behavior like an electron in a periodic magnetic flux system. But the thing is here, for this vector potential A, if you integrate the velocity around this inner radius, you get some finite value. So it means that the magnetic flux is concentrated inside this rod. But if you integrate this A around this outer radius, so you can see that it becomes 0 because the velocity is 0. So it means that the average, the net magnetic flux is 0. So it's quite similar to the Haldane model for the corner Hall effect. All right. So now, if we analyze the acoustic band structure for this system, so you can see that for an infinitely large system, then without the spinning of these rods, you can have a Dirac point at this K point. And then if you let all the rods start to spin, then you can open this band gap and form edge state. So this is for the finite structure. So in our acoustic simulation, you can see that in this case, if you put an acoustic source over here, you can launch an acoustic wave all the way to the left-hand side without coming back, even if you have obstacles. For example, you move some rods over here to form a cavity, acoustic cavity. So it doesn't matter, it still propagate to the left-hand side without backscattering. And then here, this is a step, so still propagating to the left. So it means that this is topologically protected. Even for two sharp corners, still you can go around. So it's quite similar to the corner Hall effect. Now, this photo is just for fun. This is a sculpture called Kinetic Art in Spain. So it's designed by a very famous artist called Sempier. So the interesting thing here is 10 years after this artist passed away, so in 1995, a group of material science researchers, they measured the acoustic attenuation through this periodic structure. This is the periodic structure of stainless steel. So they found that there are some in some frequency ranges, the sound attenuates very quickly. So this is the first experimental evidence for the phononic band gap in a periodic structure. Then we see the rising of the field called phononics in the past 20 years. So I always think that, well, if this sculpture is really kinetic, meaning that if these rods all of a sudden start to spin at the same time, then you can have a topological phase automatically, right? So after our paper published, then you can see that in the past 2 years, this field playing with a topological phase for sound has been developing very fast. And then recently, you can even see their topological phases for this is the quantum spin Hall effect for sound, and this is a quantum Valley Hall state for sound, both experimentally. All right. So in the next part of my talk, I'm going to talk about acoustic resonators. So a typical acoustic resonator is this so-called Helmholtz resonator. So in Helmholtz's book on the sensations of tone, he described a design to form a resonator, which is essentially a cavity with an opening. So he used it to determine the pitches of musical instruments. So a very simple resonator is this empty bottle. So you can blow it and then make sound. So it will be like this. So this is the acoustic resonator. And you can simply tune the frequency by just adding water. So you can see now I add some water. So you can see that the frequency is different. So it's very simple to tune it and then to make sound. So you can see you can also couple these two resonators together by just adding a waveguide, by just adding a coupling waveguide, connecting them. So it becomes very simple. And I must say that the first one who proposed to using acoustic resonators to build topological phases is Prof. C.T. Chen from Hong Kong University of Science and Technology. They proposed the acoustic waypoint recently. So before I introduce his work, we're going to introduce a little bit on the background. So the Weyl Fermion is a fermion that is originally predicted by Weyl in quantum field theory, but it hasn't been found in nature. But recently, people realized that we can construct similar dispersion for electron in the condensed matter systems. And what is amazing for this is this is a momentum space. You can see that this waypoint corresponds to the topological charges. What is amazing here is there will be topological surface states forming linking these two, linking a pair of Weyl points. So it's like a Fermi arc. So this is like where electrons kiss in the momentum space. And in 2015, we see the discovery of a Weyl Fermion Semimetal and the topological Fermi arcs. Because this is a highly competitive field, I'm going to highlight the publication date. So that was published on July 16, 2015. And then the next paper is submitted to PRX on July 15, and then published in the end of July. So this is what's happening in July. And then in the same issue of Science, there's a back-to-back paper describing a Weyl point in a photonic crystal. So this is done in a microwave system. So this is what happens in July. And then in September, C.D. Chen's group proposed acoustic Weyl point. So they described two structures. One is the graphite-like structure. This is the acoustic resonators connected together. So this is another design by, again, this is a graphite structure using chiral coupling. So you can see that they both have Weyl points. And then this is a Weyl point, this is another Weyl point. So let's leave it over here. Okay, there's some problem here. Let's leave it here, and then I will get back to this point later. And then this is what happens in September here. So in 2 months later, in November, there's a Nature paper talking about officially proposed this type 2 Weyl semimetals. So type 2 Weyl Fermion is quite different from the type 1 Weyl Fermion, where you can see that this is a type 1 Weyl point, this is a type 2 Weyl point. The difference is here, this type 2 Weyl point emerges at the contact between the electron and hole pockets. And then here, regarding the density of states, you can see this density state is 0, it's vanishing, but here this is finite. So it's quite different. And actually, this type 2 Weyl Fermion was originally missed by Weyl because it violates the Lorentz symmetry. So you cannot diabatically change this type 2 Weyl Fermion back to the type 1 Weyl Fermion. So it's quite different. It's fundamentally different. And then there are a lot of experiments following this proposal to confirm it. And this recent one was published 5 days ago. And then there are a lot of archive papers pending. All right. So let's get back to. So you can see that. Okay. Let's get back to Prof. Chen's proposal. So you can see that for these two structures, you have we can achieve this degenerate point here. This is a type 1 point, and this is, if you look back, you can see this is actually a type 2 Weyl point. So you can see that the first type 2 Weyl point is actually in an acoustic proposal, not in a condensed matter proposal. Of course, at that time, the type 1, type 2, they were not distinguished. So the focus of this proposal was on this design. So you can see that if you leave away from this Weyl point, you should be able to see quantum Hall effect. And then if you apply, in that band gap, you should have a topological states. So you can see there will be edge states propagating around the periphery, and this is robust against the defect. So this is the quantum Hall effect. Okay, the question is, how about this system, this type 2 system? We understand that if you leave away from this type 2 Weyl point, you will still have a quantum Hall effect. But do we have similar edge states that is very robust to the edge to the defects here? So so far the answer is unknown, and so we're gonna discuss it. Another thing is, Prof. Chen also at the same time, he also proposed another 1D acoustic structure for Z phase. So this is achieved by using a one-dimensional phononic crystal. So it's not a resonator based. So you can see that for 1D, for 3D, for different dimensions, you need to different topological systems, you need to design the structure from scratch. So the question is, can we have an approach to design the topological phases for different dimensions using the same building block, all the way from 1D to 3D. So here we are going to do that. So we start to use the acoustic resonators, connect them together. So we first start from the SSH model. This is the SSH model for hopping between AB sites. And then this is the unit cell for the acoustic structure. So you can see that these acoustic resonators, they are connected by this coupling waveguide. This waveguide is thicker. This guide is thinner. So the difference between their thickness is delta W. So you can write down the Hamiltonian for this SSH model. For the realization of acoustic resonators, you can fix the parameters for these resonators, and then for the dimerization, we fix this W to be 0.3 W. So you can see here the weights for these different coupling waveguides is W plus minus delta W. So you can see that, well, if this delta W is positive, then you can have a Z phase minus pi over 2. So the band gap is opened. And if this delta W is 0, then you can see this band gap is closed. Then if this delta W is smaller than 0, you can see this positive Z phase, pi over 2. So if you connect these two chains together with opposite delta W, this means opposite Z phase. So you will have the interface state in the band gap. So this is the acoustic pressure distribution in this system, where left and right, they have different Z phase. Well, this is for 1D. Now we are going to extend it into 2D. So we stack it along the Y direction. So this is along the X direction. These are still the dimerized chains on the last slide. On the Y direction, we just connected them with the same waveguide over here. So you can see that along the Y direction, these different 1D chains have been shifted by half of the unit cell. So for this system, you can, okay, this is the Brilliant zone for this 2D system. So for this system, you can write down the Hamiltonian to describe it, and then you can fix the parameters for the waveguide. Here along the Y direction, you can see this the thickness, the width for this waveguide is WY equals 2 WX. So now, for the tight binding model, you can plot it, and you can find that there's two Dirac points in the Brilliant zone. For the acoustic simulation, you can see that indeed there are two Dirac points emerging in this system. This is a -1 or 1 for the winding numbers for different chirality. So you can see that, okay, if you have a finite structure for the acoustic system, you can see that there will be an edge state, almost flat edge state, connecting these two Dirac points. So it's quite similar to the graphene case. All right. Now let's stack them along the third dimension. So this is the 2D systems, and then we move one dimension up. So you can see that, okay, along the third dimension, you put different waveguides to connect them. So you can describe it using a Hamiltonian here. I want to emphasize that this first item is very important, because it is this item that strongly tuned the cone shape to make it different from type 1. So then you can determine the coupling strength, and then from here you can determine the real size of the acoustic structure. So here you can choose different the weights for the coupling waveguide. And then for the tight binding model, so you can see that if I choose a particular KZ in the Z direction, so you can see there are two degenerate points in the Brilliant zone over here. So these 2 points correspond to the wave point. And this is the acoustic simulation. You can see indeed there are two degenerate points here. And if you zoom in at one wave point, you can see the cone shape is strongly tilted. So indeed, this acoustic simulation, it shows that the cone is strongly tilted. And if you plot the density of states, you can see that, or here, this is finite, it's not vanishing. So here, now, so it means that in the 3D Brilliant zone, you will have 4 waypoints in the Brilliant zone here. So if you project the space, if you project the Brilliant zone along the kx plus ky direction to a finite system, then you can find that, okay, this 4 waypoint is projected to this to this momentum space. And then if you scan ky, if you scan kz along this cut, you will see that there are indeed there are two edge states emerging in this band gap. So, the difference comparing to the type 1 system is that in the type 1 Weyl point, if you leave away from the Weyl point and open the band gap, you will have two edge states. One is if one edge state on the upper edge is propagating to the left, then the edge state on the lower edge must propagate to the right. So this is determined by the chirality, dictated by the chain number. But here you can see both of these two edge states, they propagate in the same direction. So this is determined by the strong tilting of the cone shape. So this is very unique to the type 2 systems. And if you scan KZ along this cut 2, you can see that there's no band gap, there's no edge state in the band gap. Now, if you fix the frequency at the Weyl point, there's no Fermi level at the in an acoustic system. So if you fix the frequency at the Weyl point and try to trace the edge states, in the momentum space, you can see that indeed they can link up these two Weyl point and form Fermi arcs. So you can see that here these edge states, they are topological in the sense that they can link up these two Weyl points and form Fermi arcs. But on the other hand, they are not that robust comparing to the type 1 system. Remember, in type 1 acoustic systems, you can see there's a edge state propagating around the periphery, which is very robust against the defect. But here, for this kind of type 2 edge states, you can see that these edge states emerge in an incomplete band gap. That means that if you have a defect, this defect can scatter the edge state into the bulk. So you won't be able to see a similar robustness comparing to the type 1 Weyl system. All right. Now, let's go back to the Haldane's paper. So you can see that the first photonic analog starts from Haldane's model, and then the first acoustic analog also starts from Haldane's model. So do we have, can we construct Landau levels for sound? So the immediate question is, can we have Landau levels for photons? There is indeed a proposal for photonic Landau levels, but so here you can see that here this is essentially a bunch of waveguides in the z direction. So in the XY cross section, this is a honeycomb structure. So if you shine a laser beam on it and then follow the propagation along the z direction, so the z axis plays a role of time. And then you can see, plays a role of time. And then you can see the momentum kz plays a role of energy. So if you plot the momentum kz versus kx, ky, so you can see you form a Dirac point. This is the momentum spectrum. So now, if you play the string engineering, which is developed in graphene electronics, to distort the lattice, then you can form an effective uniform magnetic field, and then you can form the Landau levels for photons. But this is not really energy quantization, this is momentum quantization. And then you can see that the problem is you need to use an ideally infinitely long structure to simulate in the 3D, to simulate a 2D phenomenon. So it's complicated. So in our case, we just use acoustic resonators to hook them up from a honeycomb structure. So you can see that in this case, this is a unit cell, this is a top view, this is a side view. Then you can form a Dirac point, and then you distort the lattice to form an effective magnetic field. So you can see there's Landau levels over here, okay? And then you can see this band gap is proportional to square root b. B is the effective magnetic field caused by the string engineering, and this n is the index of Landau levels. So this is the acoustic simulation of 11,600 resonators. But in the reality, in a feasible experiment, we need to use a relatively smaller number of resonators. So let's say if we consider 262 resonators, and then you can see that this is a structure. So without any string, without any distortion to the lattice, you can see there's a continuous spectrum. And if you apply the strength a little bit, you can see the Landau levels with the 0th order plus minus 1 order. So you can see the band gaps start to emerge. And if you increase the strength, then you can see the band gap is even wider, wider. So this roughly satisfies the condition of square root b n here. Now, in our in the laboratory, okay, we really did one demonstration of the Landau levels for sound. So very simple. You just choose a piece of metallic plate, and then you start to drill holes on it. So this is a honeycomb structure. We put a speaker over here, and then we put a microphone at the corner to measure the transmission of sound. So this is a simulation. This is the experiment. You don't see a clear band gap over here. So this is a continuous spectrum. And then you start to distort the lattice over here. So this is the 262 resonators. And you can see that there are two band gaps emerge over here. So this is the band gap between the first order Landau level and the plus minus 1 Landau levels. And again, you can see in the experiment, you can see there's a two band gaps here. So if you further increase the distortion, then you can see the band gap is become wider. Okay, so this is the first demonstration of acoustic Landau levels. This is the Landau energy quantization for classical waves. All right. Right, let me summarize. So we can see that this is the quantum Hall effect of, we first discussed the quantum Hall effect of sound. This is follows the flow-induced gauge flux. And then we have wave-points of sound. This is for type 2. And for Landau levels, this is string-induced uniform magnetic field there. All right. So thanks a lot.
Started sigma x and sigma z, Pauli matrix and some coefficient. You show one of the slides.
Yes, can you say it again?
One of the kindly open the slides again that you propose the Hamiltonian H model
okay.
sigma x and sigma z that you have started earlier version. Yes. If you want that, I can.
So I don't quite understand your question.
If you want that to study the geometric phase of this corresponding Hamiltonian, I will be able to calculate this geometric phase within 5 steps.
So again, I don't quite understand the question.
If you want to study the geometric phase of the gap phase of this corresponding problem, you will be able to calculate the whole geometric phase within 5 steps.
5 steps. Yes.
Okay.
No.
I just, it's just an idea that, like in magnetohydrodynamics, one couples the electric and the fluid field together. So supposing in such a thing you could couple the sound and the light field together and get sort of sound and light vortices on the same footing or something like that. Like, have you ever thought it would be in the continuous version and it would be, you can couple them together and get opto-acoustic.
Yeah, this is a very cool question, but so far we haven't started to think about it. If you couple both the light and sound in the same time, it would be very cool. Right, the answer is so far we haven't started to think about it. Regarding the previous comment, I think the response is derivation is one thing. The physics of another system is one thing. So you can see that here, you can do very fast derivations for the SSH model. This is a very standard model. But one thing is, first of all, this is for sound. It's a very different physical system. Another thing is, the benefit here is, for each resonator, you can open it. You can see the wave function. You can see what happened here. So for example, for the edge state over here, you can really detect it by just put in a microphone here. So you can really measure it. This cannot be achieved. Okay, at least it's very challenging in the condensed matter system because you won't be able to see the waveform here. For the acoustic wave, the benefit is it's a classical wave. You can see that there are a lot of acoustic instruments there. So you can measure both the amplitude and phase. Right. Correct. But for electron wave function, well, you won't be able to see anything, at least for the phase there.
So I wonder if it's possible to make these resonators time dependent in some way, and then to study like the Flux topological insulators.
Yeah, there are already some proposals using the time modulation to achieve different systems. Yeah. Yes, it is possible, yes.
Any other questions from the younger members of the audience? Yes.
These band diagrams are quite risky because in the continuum you have all the flat bands. So in the continuum you have no flow of your energy, I would say. Like, how does it make sense? The continuum of your band, they are all flat bands. So I can, like, just by looking at it, I can say that in the continuum nothing propagates. Right? You have the continuum bands in the top, the blue bands, the figure at the bottom left corner.
This is for the interface. So you have already contended two trains together. So it's quite different from here. It's very different from here.
So what does this band diagram correspond to?
Here.
Is it one-dimensional? Because you have drawn a one-dimensional curve,
Yes.
one schematic.
Yes,
here.
it's a 1D system, but you have two trains connected together.
Right.
So the left and right, they have different Zhang phase.
You have different hopping like amplitude
Right, but
there.
here the difference is for the left-hand side you have delta W positive. This corresponds to the positive Zhang phase. On the right-hand side, this is this case here.
Right.
So in between there is a phase transition here.
You close the gap in
Yes,
between.
yes, correct.
But my particular question was that the band diagram you have drawn here, what does this correspond to? You have drawn K versus like some energy, I would say.
Yeah,
so this is for a bulk system, infinite system. And if you have an infinite system, and if all your bands are flat bands, then there is no propagation of energy within the system.
There is no propagation. In this case, there's no propagation here.
It's fully dimerized.
Right. There's no propagation here.
Right.
This is a 1D thing, yes.
And on your slide 33, 2 slides later, could you please go there? This is slide 31.
Yes. Slide back. Okay.
Okay.
Right.
There you have used Pauli matrices, and your D0 is like I was quite surprised that your the dispersion depends on D0, because usually we throw away the D0, and
right.
D0 is usually like some shift of my eigenvalues. We don't care about them.
Correct.
But here your D0 depends on K, and they're both the same. So if you have two sublattices, and if the two sublattices are identical, then what's the point in using a Pauli matrix instead of just a scalar?
This is the essence of type 2 system, because it is this item, D0, which can tilt the cone of the regular Dirac-like cone shape. Right. So without this item, yes, generally people just throw away this first item here. That's why previously, even for the first proposal of acoustic waypoint, people have ignored that item. Although we can see that this is for acoustic simulation, we see this structure, but if you throw away the first item, then if you consider all the systems in the type 1 Weyl Hamiltonian, then they behave the same. But actually not, because the first item is very important. It is indeed that item that tilts the cone shape. So you cannot ignore them there.
And what's the physical motivation behind having a diagonal entry that depends on having this strange shape?
The motivation is, okay, this goes back to the type 2 system. This type 1 Weyl Hamiltonian was originally predicted by Weyl. So when you talk about Weyl Hamiltonian, this is the type 1 system. But for type 2, this only exists in the condensed matter and other systems. It doesn't exist in quantum field theory because it violates the Lorentz symmetry. So you cannot diabatically change this back to that. In condensed matter system, you don't need to respect Lorentz symmetry. That's why for the type 2, it can exist in condensed matter, but not in the quantum field theory. So that's why Weyl actually missed that point.
Thank you.